the agenda of this session is that there are certain common trade-offs that are made when designing applications using distributed systems. We want to see those trade-offs. We want to identify them. And what we want to do is we want to see if we can take some of the information that we get today and probably, use it for our day-to-day life as a software engineer. So let's start. The first trade-off that I want to talk about is very common, and it's a pull versus push trade-off. Okay. So usually this happens in systems which are notification systems. For example, if you have something like an Instagram server, which has users sending posts. Okay, there's another user over here, and they are following this user. So there is some sort of relation that this user has with another user. Similarly, there's another user who's following this user. And there's hundreds of people who are probably following this user. This is a common Instagram situation. This person might be Brad Pitt or Barack Obama, very famous. Now, what happens is if they make a post on Instagram, you have to send a notification to every follower. Now, this becomes an engineering challenge because this is where we'll start seeing trade-offs now. The engineering challenge is you need to make some sort of system which can send notifications to all the users who are following this celebrity. Okay, and the application we are thinking of is Instagram, but you can think of a 911 dispatcher also. You can think of Twitter. You can think of any social media app which has some sort of a notification system. So we are noticing that there is one non-functional requirement that we have, that notifications should be sent fast, should be accurate, and should be sent to everybody. That is something we need to do. And there is an engineering challenge here. What is the engineering challenge? If Brad Pitt sends a message, what's going to end up happening is millions of people will need a notification quickly. That means that if we use some sort of a simple approach to this problem, a brute force approach, let's say, what's going to happen is we'll have this Instagram server, get this event, a post, convert it to an object, which is a notification object that Brad Pitt has made a post on so-and-so time, and you want to send this to their timelines. This notification will need to be pushed to every user who is following Brad Pitt, which is effectively in millions. Okay, so millions of notifications will need to be sent, and you want this to be fast also. You want people to get the notification quickly. If we do this, if we use the simple approach, this is going to cost a lot of resources. You'll need a lot of bandwidth. You'll need a lot of possibly processing, and it'll put a lot of load on your system. So that's the problem with the push model. When you push notifications in a notification system to all clients who are interested in a certain type of notification, it doesn't work because there is too much load on the server. Okay, this is the problem that we have. How do we solve this? Anyone on the chat who wants to attempt a possible solution? It's actually quite simple. It's just here, the pull. Pull would mean that if you have all of this, the black lines are all pushing. So I'll remove them. And I'll actually draw this separately. Now let's imagine that Brad Pitt sends a message to a popular social media app, which has to, in real time, give notifications to all of their followers. So the blue line shows a push notification. This is being sent to millions of people. That's a bad idea. So we are not going to do the blue line thing. Instead of sending notifications from the server directly after every event, we are going to ask the user to poll the server that we have. Okay, so maybe someone is offline, they come 10 minutes later. Maybe some people are not interested in ever opening Instagram, they just follow people for the sake of following it. So all of those use cases will help us reduce the load on the server. The thing is, if Brad Pitt made a post here, so this is the celebrity, and this is our server. Now, instead of doing this, pushing, we are instead asking them to poll our server. So when they want to get a notification, they're going to get a notification. Okay, this is the pull model. You're pulling from the server. We just changed the direction of communication. Okay, why is this such a big thing, and should we always pull? Right, because it seems like push is never good. No, in some cases, push is good. If there's a person like me who's making a social media post, there won't be that many people who are interested in this. So in that case, if someone logs in and they ask the server that, what messages did Gaurav send, that's going to create some load on the server beforehand. So what you want to do in that case is you want the server to push a message. Okay, so for less popular, or let's say for normal people who have a few thousand followers, you want to push for low activity, just low followers. Yeah, if the user has low followers, you push. If they have a high number of followers, you pull. A simple idea, the trade-off being, if you want things in real time, you want to push. If you want things done efficiently, you pull. Okay, when it comes to a notification system. And I think nearly all of us have worked on notification systems or chat systems which use this kind of an architecture. How do you send a message from one stream to multiple streams? How do you broadcast efficiently? Efficiency, yes, that's when you use pull. When you use for real time, that's when you use push. In a chat system with just one-on-one chat, you always want to push. Okay, so that the other person gets a notification on their chat app. Right. So this is the simplest trade-off I wanted to start with, also to give you an idea of what's going to be happening in this session. You're seeing that there's a distributed system where we are needing to make one engineering trade-off to satisfy some non-functional requirement. In this case, the requirement was that our users need to get notifications quickly. In this session, that's what we're going to do moving forward also. Okay, any questions on this? Any thoughts on this? I'll take a minute. In case you have any doubt on the idea or what we are going with in this session. Okay, great. So this is the push versus pull trade-off. Can you give me a hybrid approach? What's happening till now is we are saying that if people are not very, we have designed a system where in some cases we have to send a lot of notifications. In some cases we have to send few notifications. And based on the requirement, we are changing our algorithm of either pushing notifications or pulling from the server. So is there any approach that we can use, which is a hybrid approach, which has the best of both worlds? And we can tune it according to our requirements. Because the trade-off, meaning design trade-offs here, are about fulfilling your non-functional requirements in the best way possible. So it's not necessary that we can choose only one out of these. We can choose both at the same time. Okay, Joe was saying, so you can buy the efficiency by saving data on the server who needs the notification. yes, we are saving data on the server. Yes, we are saving network. So instead of us sending a million notifications, which is going to cost a lot of network, we are instead asking for the user to ask for the notification, like waiting for the user to ask the notification. You send just one notification to them. Then someone else comes to you. The same notification is asked. Brad Pitt, the post. You give that to them. So in this way, there's not a huge amount of load together. If you see the server graph over here, if I start pushing notifications, the moment, let's say this is normal, Brad Pitt makes a post over here, the server is going to spike till here if I do a push architecture. On the other hand, if I have a pull architecture, what's going to happen is the server load is going to be the same over here. When Brad Pitt makes a post, oh my God, okay, there's going to be a bump, but it's going to go up slightly and then eventually die down. So this is much more manageable. Your cost is also lesser. And the load on your external systems is also lesser. If you have any downstream systems which are, using your current server, they won't need to wait a lot. In general, it's good. Okay. Hesam is saying push for some and pull for others. Yes, that's true. Marco is also saying register a listener and a single push. Okay, these are all good ideas. Now this is a good idea because you have, let's say, Instagram here, and you have some people who are really, really popular. The moment they make a post, you don't want to hammer everybody with notifications. So what you end up doing is you cache that. You cache that notification. When their followers ask for the notification, when they ask for their timeline, you know that they have, they have some sort of relation with this person. Maybe they're following them, maybe they're connected to them in some way. It could be LinkedIn also. What you do is you notice that connection, and then you say, all right, because this person is a celebrity, because there's a criteria that if they have more than 9,000 followers, then they're classified as celebrity. I know that their posts will probably be found in the cache. The recent posts will probably be found in the cache. So get your timeline from Instagram and also hit the cache, get those posts from this user as a response and fill up your timeline. That's what you'll see on your mobile now. Okay. For everyone else, let's say this person is not very popular. They are following this celebrity, but they themselves are having maybe just 50 followers. If they make a post, we find all of the followers for this person, let's say person number 3 on our database, we'll see that person number 3 is followed by person number 1, 2, and 3. I mean, they can't follow themselves. So let's say 4. So our system has these 3 users, 1, 2, and 4, who need to be notified that person number 3 has sent a post. Okay, please send them the message. This is a push. This is good because it's real time. It happened immediately. Also, maybe you're saving on the load that would be coming up later. You're doing your tasks as soon as possible. So this is a hybrid approach. You have push in one case, and you have pull in the other case. It's actually not coming from this celebrity. The celebrity is not pulling anything. The people who are following them are pulling. Okay, so that's the hybrid approach. I think we got a couple of answers in the chat, which were absolutely right. Perfect. Okay, so, okay, Sen is asking, what if the person is not a celebrity, but fortunately his post got viral in like seconds? Can the same strategy be applied? Yes, yes. In fact, you might have, the more intelligent your algorithm gets, the better trade-offs you're able to make. One of the things that you can do is, if this person has a lot of followers, that's one criteria to consider this a celebrity post. Okay, there are people who have 1 million followers and nobody watches their posts. That is also possible. Maybe they have been banned. Maybe there's not enough activity in their followers. Their community is not very active. In which case, it's fine. You don't classify this as a celebrity post. That is possible. So that's point number 1. So for users who have an active audience, that's when you want to classify them as celebrities. The second thing would be, if a post is getting really, really popular, you want to cache it. So this cache that you have can have a criteria that, is this to be sent to 5,000 people? Okay. Sometimes that comes from the follower count. Sometimes that comes from your recommendation engine in the backend. So you can mark a post as viral, or sometimes a cache can handle this by itself. I mean, you have caching policies through which popular posts can go into the cache. But even then, you don't need to broadcast immediately, right? You don't need to fill people's timelines quickly. That can happen a little later. It's a good question, though. I mean, when do you fill people's timelines? If it's a popular post, don't you want everyone to see it on their timeline? Yes, you do. So the recommendation engine has to bump up that post into this, into people's feed. Yeah. Syed is asking, depends on the notification size we decide to pull or push, right? Yes, it does depend on the notification size, whether you want to pull or push. It depends on the popularity of the post, whether you want to cache it or not. Okay. Notifications, I mean, if you have to send 5 million notifications, that makes it a popular post by itself. Awesome. Okay, so this is one engineering trade-off that we have. You're seeing that this is a non-functional requirement. I could come and say that I'm meeting all my functional requirements by using a brute force algorithm. There is no problem. Technically, there is no problem. But practically, of course, it's going to take hours before people get notifications. And it's going to cost a lot of more resources if you're going to use the approach over here, right? The previous approach. We don't want that. We want the smoother approach. The blue line, yeah. Okay, perfect. Now let's go for the second trade-off. And this is a trade-off which is quite common, but is not visible till something big happens, some problems start. So the second trade-off is throughput versus latency. So let's take a computer and let's slice the time that it has to do tasks this way. Okay. Now, if you have a task A, which is a computationally heavy task, and you assign all of the time slices like this, then there is the throughput here is going to be 100%, because all of the time that you spent, your processor spent, is spent on doing a task. Okay, so this is good. On the other hand, if you take your operating system time and you slice it, if you take your application time basically, and slice it and you make it something like this, A, B, A, B, and A. What is happening in each of these black lines is a context switch. Okay. There are some things I'm expecting implicitly. If you run A on a single thread and your computer just has one thread, at this point, your throughput will be 100%. Yeah. If you're running multiple processes in one computer and you're doing a lot of context switching, that's a bit of a problem. It's not a problem, but your throughput is going to go down. This is going to cost you something. Right? So we should always have throughput as high as possible. I mean, you want to do jobs for, you want to run your computers at 100% efficiency. We want high throughput. That is known. Okay. What about latency? If you run your processor this way, where you do one task A and then another task B, your throughput is going to be pretty high. But if a request comes for task B, which depends on B. How long does it have to wait? It has to wait from this point, T0, to this point, T1, for the task to be picked up. Then it has to wait for a response. Maybe that comes very quickly over here, T2. Okay. So ideally, what should have happened is you should have had the response time of T2 minus T1, but instead the response time is this entire section, which is T2 minus T0, which is much larger. So what happened here is throughput actually is high, but latency is also high. Latency is the time taken to answer a request. Okay, the response time basically. So latency is also high. This is bad. We don't want high latency. We want low latency. To reduce latency, so I hope this point is clear. If you have any doubts, you can post them in the chat. The idea is we want to run our system in this kind of an architecture, right? The first type, where you run tasks in sequence, complete A, complete B, and then move forward. But if you do that, there will be no concurrency. Okay, and if there is no concurrency, if you're not handling requests, concurrently, it's going to cost you in terms of response time. Latency is going to go high. To reduce latency, we can use this kind of an architecture, which is on the second part of the screen over here. When you do this, your context switching is high, but latency actually goes down, because what ends up happening is when you get a request for B, and even if you land up over here, this is T0, you can see T1 is happening much sooner. This gap is really small. And then you have some time to respond to the request, which is T2. So T2 minus T0 in this case is much smaller than the case over here. Okay, because you're doing context switching, because you did not wait for all this time for A to finish. Right? This happens in many places. It happens in request response, when you're dealing with requests in a server. But one place where this is super important is garbage collection. Yeah, in garbage collection, you have an application fighting for resources with a garbage collector. So if your garbage collector is running, if it stops your application and it runs, then what ends up happening is your application is running till this point. It has to stop. It goes brain dead. It has to sleep for some time while the garbage collector is running, so that it does not corrupt state. And when the garbage collector is done running, again, the application starts running. So overall, your latency, instead of being X plus Y, so this is latency, instead it becomes plus Z. For no fault of your own, it becomes plus Z. Okay. So what you want is you want to run your garbage collector concurrently with your application. But the more you do that, your throughput goes down. So it costs you more resources. 10 computers, if you're running at 90% throughput, then you can make the claim that with 9 computers, I could do what 10 computers are doing right now. So your costs are going up, your throughput is going down, but your latency is also reducing. That's the trade-off. Okay, if you want to reduce latency, you have to reduce throughput also, in some cases. Okay, any questions on this? Any use cases that you have come up with? Any situation where you have actually seen this happen? Or any doubts on this, of course. That's more important. If you think of it, the best way, the lowest latency is going to be for every user's request, have a separate computer. Like, this is crazy, of course, but I'm just giving an idea over here. You have a request, you send it to one computer. If you have any other request and any other computers dealing with anything, just send it to the next computer, right? This is going to cost you a lot. Of course, your latency is going to be very, very low. It's going to be your execution time, right? There is no wait time involved. So you have minimized latency, but of course you have maximized cost. You have minimized throughput also. That's the other way to look at it. And the worst way would be just to have a single computer and allow all the requests to run sequentially. In this case, you have maximized your throughput, you have minimized, and you have maximized latency also. You might be having this thing that, hey, I can run the things concurrently, can't I? Yeah, you can. You can run them concurrently. That will reduce throughput too, because there is some context switching going on. So latency went down, but context switching caused the throughput to go down also. Okay, then. Let's go for a more commonly talked about trade-off. Probably the most common trade-off in distributed systems is consistency versus availability. Okay. So what does this mean? This is applicable mainly for distributed systems. So I'll add another box over here. Okay, I'll get rid of this. Firstly, can someone on the chat tell me what is consistency versus availability? If you have read the CAP theorem, you don't need to necessarily, this is a trade-off where data consistency, I'm talking about data consistency versus availability of a service. This is what I'm talking about. I'll wait for 2 minutes. If you have any doubts with any of the things earlier, like throughput versus latency or pull versus push, you can post them now on the chat. And you can also post your thoughts on what is this going to be about, data consistency versus availability of a service. Okay, Mark is saying that having one truth versus having a good enough response quickly. Yeah, that sums it up quite well. Ramdas is saying that, banking system versus Facebook. Okay, that's interesting. Pascal, consistency might decrease when focusing on availability. Okay, that is also true. Sen says every time you push data to different places, the data has to be the same in all places. Okay. Yes. Yes. A lot of this is interesting. I'll pick the first one, which is banking system versus Facebook. Ramdas has posted this, and it's the right thinking. But a banking system, like what happens in a lot of system design interviews, is we look at the entire system as one black box. So even before starting designing services, there is a question of, am I going to make this system consistent or available? Right? I would say maybe instead of looking at the entire system as consistent or available, think of each service being either consistent or available. Even a banking system can have notifications which are slow. Okay, it can have some calculations which are being shown, which are highly available or not, but not very consistent. While Facebook might have certain systems which are highly consistent and not very available. Okay, so instead of imagining the entire block, this system as consistent or available, think of each service as being highly consistent or highly available. That will bring you closer to the functional requirements. Okay, now the next part was having one truth versus having a good enough response quickly. Okay, let's take an example of that. Let's say you are running the likes system on Facebook. Everyone comes and likes posts. You are supposed to tell how many likes have come in each post. So a highly consistent system is going to give you data. Let's make a table. So let's say there is in this like ID, there's a post ID. So you have some sort of a post ID, and you have a user who has liked this post at a particular time. At any point in time, if you want to know how many people have liked a particular post, you do a select star from likes table. Let's call this likes table, where post ID is equal to a placeholder. Okay. And if you have just one copy of this data, it's highly consistent, but it's not very available. If this data crashes, if this database crashes, then nobody's going to get the data. Okay, so it's not very available. On the other hand, if you have a copy of this data, which is being periodically updated, so you have rows 1, 2, and 3 over here, and at this point in time, you just have 2 rows over here, 1 and 2, and the same schema over here. What's going to happen is, if this data copy crashes, that's okay. What you do is you do the available thing. You pick this data copy and say how many likes exist for this post, and the answer might be 2 instead of 3. So it is not consistent, it's not right, it's inaccurate, but the system is still working. And especially when you're building a system of reactions, likes, things which are not very important to note down, that's when you probably want to go for availability as much as possible. When you want to build things where sharing information accurately, noting down information, being right more than being available is important, that's when you want to go for consistency. So where is the trade-off? I mean, there is some trade-off we can see, but there are only 2 options we have. It's not a trade-off exactly. The trade-off would be that you have a distributed database or some sort of a distributed system where the data being stored is in 3 nodes. So let's call this node number 1, 2, and 3. Whenever you get a request for some read operation, right, like an SQL query, select star from likes where post ID equal to something, you query the table 1, you query database 2 and database 3, they give you responses. Okay, and they're talking to each other and keeping each other consistent. Let's assume that they have some sort of a protocol to do that. They periodically share data. Let's say the response from here is equal to 5, the response from here is equal to 6, and the response from here is equal to 5. What do? You take the majority response. Okay, so this would be called quorum. You have multiple boxes, let's say n boxes, and a certain number of boxes have to successfully give the same read response for this to be a safe read request. How you pick the response is kind of up to you. You might have a majority response. You might be that 6 is actually more updated, having the highest timestamp. So you pick this up. That is also possible. Okay. And what happens when you do a write request? When you do a write request, I mean, in a read, firstly, is the read request making sense? You have a set of data nodes, all of them talk to each other and keep each other updated, but there might be some mismatch. So whenever a read request comes in, you ask all 3 nodes and pick the majority or pick the latest response. So your system is not very, it is reasonably consistent and reasonably available is what I should say. The chance of it not being consistent is really low. Okay, let's take a minute to think over this. What would happen in a write request? Can we do something similar or should we do something different? Oh, actually, let me take a poll if that's possible. I don't think it is. Maybe it is. I just want to know if, I mean, how many of you already know about quorum? Otherwise, I'll be asking you the wrong questions. Okay. Hisam is saying it does not matter for write request. Ah, okay. Okay. So what happened in the read request? I actually had 3 nodes, n was equal to 3. And I said, please read from 3 nodes. So of course, it's going to be right. When there's a write request, if I let's go back to the read request. Let's not go for write so quickly. Go to the read request. If one of these nodes fails, what happens? I could fail the request. That is one thing I could do. I could also take 2 nodes, the remaining 2 nodes, and take their read request and then, you know, try to get the best out of that. So if node 3 goes down, I get 2 answers, 5 and 5. So I take 5 and I'm happy. This was my response from the system. But maybe 3 had the latest data. It had this 6 value and it never got read because 3 collapsed. Right? Instead, I did a quorum. I saw that the majority 2 are surviving out of 3. They say it's 5. I go ahead with 5. So if my criteria for a successful response read request is 2, R equal to 2, then I might lose out on some consistency. Okay. We are seeing that could happen. Okay. A write request is also handled very similarly. In a write request, you can say how many writers should I have? So if I select 1 writer, in this case 3, then the write request might go over there, update the data. When it crashes, I will have some problems. 1 and 2 might have inconsistent data. Okay. So read.
Damit bist du fit für die.
I'm sorry. I didn't catch that. Okay, I think we had an answer almost. We can fix it. Yes, it is readers plus writers have to be greater than n for us to have perfect consistency, strong consistency. Right? Because if you're writing to at least 2 nodes, these 2 nodes, and there are 3 nodes in total, okay, and you're reading from these 2 nodes, there has to be some intersection. In the Venn diagram of readers plus writers, or the pigeonhole principle, whatever you like to think of, there will be some intersection amongst readers and writers for every request, every data update. So you will get the latest data. If you expect at least R readers and W writers in an n-node system. By tweaking this, by tweaking the number of readers and writers, you can make your system read heavy or write heavy. Depending on that, you can tweak these 2. And the other thing you can do is, if you want strong consistency, go for this guarantee. If you want for weak consistency, you can go for this guarantee. Readers and writers can be less than n. You don't really care. You don't really care if you return 5 or 6 over here. You just want kind of recent enough data. It'll work. If one of the systems goes down or does not respond in time, or is not even asked, doesn't matter. You know, you're basically going for high availability, low response times instead of high consistency, which will cause a high response time and more resource use also. Okay. Okay, I think there was a glitch. Fine. I hope, am I audible now? Is everything fine? Yes. Okay, perfect. So this is consistency versus availability. Very commonly asked, very, you know, whenever you're designing a system, maybe even with your team, you might be thinking about, should I make my system, not even the entire system, it's like one service or one part of the service, should I make this consistent or available? What kind of trade-offs can I use? There are some abstractions which really help you make good engineering decisions, like any kind of a distributed cache or a distributed database can help you store state in a way that you can make these trade-offs correctly. So an example of a distributed database is going to be Cassandra or Amazon DynamoDB. If you are looking for a distributed cache, global cache, that would be Redis, and there are other caches also. Okay, I'll wait for another minute. If you have any questions, you can post them on the chat. Okay. Is there a difference between a node going down and returning a different value? Yes. Yes, there is. Let's redraw this part of the system. Let's say you have 3 nodes. And you made a read request. So the moment you make a read request to the cluster, here, 2 has a value for itself, which is 1. It asks the value of 1 also, which is 1. And 3 probably has a different value, let's say 37. Okay, let's take the 2 scenarios. You ask a value for a particular key, which has 1 and 1 here and 37 somewhere else. So 1 responds with the value 1, 2 has a value of 1, and it sees that 3 is not responding. Tries to make a request, it fails. So in this case, 2 confidently says the value is 1. Okay, the quorum or the answer returned is 1. On the other hand, if 3 returned a different value, if the request actually went through and 3 returned a value of 37, what happens here is 2 is going to see I have 2 values, 1 and 1. By majority, 1 should win. But if 37 is a more updated value, so along with this value, if it sends a timestamp of update, let's say this is 56, and over here, the timestamp of update is 10, and the timestamp of update is 12, then 2 can make the decision that, hey, this is the latest value. So maybe I should pick this up. Okay, so returning a different value might change the result. While if the same system is down, the result can be different. Okay, so until now, what we have done is we have looked at some common engineering trade-offs when sending notifications or any kind of messages, broadcasting them. What are the benefits of the two? Similarly, in throughput and latency, what we have done is we have seen that, how can we judiciously use the maximum amount of resources we can in the computer without losing out on our response times. So for trade-offs, yes, if you want to increase latency, or rather, if you want to increase throughput, you probably will have to sacrifice a little on the latency side of things. Okay. And then finally, we came to this third part, which is if you're looking for high consistency, the availability of your service can go down, because if you force readers plus writers to be greater than the total number of nodes you have, of course, there's going to be an intersection. But if you don't find at least these many readers, at least, if you say readers is equal to 2, and out of the 3 nodes that you had, only 1 is up. So your read request will fail. So availability will be off that time. But what you're doing is you're doing a trade-off over here. Okay. The final trade-off that I want to talk about is trade-off number 4, replication versus something we saw right now, consensus. Okay, so consensus means you have a request in your system. Your system has multiple players who look at the request, give responses based on the data that they have, and then there is some sort of decision which is made, which is returned, similar to what we saw above. The consensus protocol being used above was quorum. Okay, what is the data that I have for this request? That's one type of response handling. Another type would be replication, where you have a data node and you have another data node which is a copy of this earlier data node. So this is, let's say, this has the value 10. Every second, the value over here is updated. So 10. The moment I make it 20, it's going to take a second in which, you know, these two nodes are going to be inconsistent for a small period of time. And then this is going to convert to 20. I think a lot of you are thinking about ahead logging and a lot of the other stuff through which you can handle this. But for now, let's look at this simple idea of replication only. Okay. So consensus or replication. What do you see are, I mean, which architecture would you go for? It depends on the system, yes, but which one would you say has higher latency or requires more resources? Is it consensus or is it replication? Which one requires more? Which one has higher latency? Yeah. So the question is it higher here or is it higher here? Okay. More resources are required in replication. Okay, that is possible. So that's an interesting answer, Max. Higher latency for replication. Okay. I don't know. High latency for replication. Okay. So let's have a look at this. What is the latency like? So when I'm talking about latency, let me clarify. This is request latency or response latency, rather. So I send a request over here to this system. How much time will it take for it to give me a response? Versus sending a request over here to this system, how much time will it take to send me a response? High latency for replication. Okay. Okay, send. Yeah, if it's response, then what's going to happen is in this kind of a system, usually what you do is you just ask the main node, the leader node, what is the, so leader won't be the right word to use here, primary, let's say. The primary node, what's the data? 20. Okay, give a response immediately. So the latency here is a little low. While if you ask the same question over here, what is the data? 4 nodes will be hit, of which 2 will answer. And then there'll be a decision made and then a response will be given back. So it's going to take some time. 2 nodes might answer. As you increase the number of nodes which need to answer, there'll always be slackers. There'll always be people who take 10 seconds to respond. So the first few nodes answer quickly, and then there is one node which answers very slowly. This is also a problem. Okay. So what ends up happening is latency is high when you're doing consensus. Okay. Latency is usually low for replicated nodes. What could be a problem? Okay, now let's take another another non-functional requirement, and let's see what the trade-off is. So latency, the winner is replication, low latency. What about availability? Which system has higher availability? Yeah. So Rui and Ralph, you got it. The system implementing quorum. Okay, Max is like replication. Max, you are kind of right. In some cases that is possible. If you have replication, this node goes down, you send a request, that's fine. This node will come up and you'll get the answer of 20. But if this node goes down also, you have a bit of a problem. So availability here will be you can afford 2 nodes to fail. While over here, you can say that I just need 1 node to respond to me. Readers is equal to 1. And the number of writers is also equal to 1. You have 4 nodes, n is equal to 4. N is greater than readers plus writers. So this is a low consistency system. It's an eventually consistent system is what you'd like to call it. Your availability is high because even if 2 nodes go down, like over here, so if I take down 4 and if I take down 2, that's okay. 1 and 3 will respond. You just need 1 reader to respond and your system is still available. Okay, great. So in terms of availability, this system is high. In terms of latency, I think this system wins. In terms of cost, expenses, which one would you like to choose? This would be the last question. But the idea is like replication versus consensus. We think about leader election protocols. We think about quorum. What is one thing which is a bit of a problem here when compared to simple replication? So let me write that down. Cost, which is higher? Is it in replication or is it when you're having some sort of consensus protocol? Yeah, quorum is more expensive more often than not, because even if you shard your data in different nodes, you probably want a replica of that shard, okay, in another node. So that would have been very simple over here. So you would have a primary and a replica. But in this case, there is some engineering complexity also involved. You don't know where the replica for 20 is being stored over here. When you have 1, 2, 3, and 4, that's a bit of a problem. The network calls are a bit of a problem. You have to make multiple network calls for every read and write request. There is some sort of decision making you have to make. So the cost is high more often when you have some sort of consensus protocol running, some sort of leader election protocol running. Yeah. Okay, so that's perfect. I think we have picked 4 trade-offs in distributed systems. Replication versus consensus. There is consistency versus availability, throughput versus latency, and pull versus push. I hope this helps you, in your day-to-day engineering life to make good decisions. Thank you for this.